So, let me rewind some of the discussion that we have already done. We know that the Hall plateaus are quantized, and we have taken a 2D electron gas and have put a perpendicular magnetic field, and when you calculate the Hall conductivity, the conductivity is or the resistivity, either of them is found to be quantized at values that are integral multiples of h over e square or e square over h. Let us just talk about the conductivity for the moment. So, it is integral multiple of e square over h, and these integers are very robust. They do not go away with disorder, and the system, as I said, does not possess a translational symmetry or a time reversal symmetry. Still, these plateaus continue to exist. They are resilient to these external conditions that we have spoken about. This is of course a fact. We need to understand deeper, that is, why do they survive even though the symmetry protections are not there, and in fact it is because the symmetry protections are not there the plateaus actually arise. And some of the physical reasons we have seen that there are disorder that plays a role in broadening the Landau bands, and as you know the Landau levels move, or as the magnetic field is increased, the Landau bands kind of successively cross the Fermi level, and that is where they spend some time while crossing the Fermi level, and one sees that there is a plateau that arises. Now, we have said that these quantization of the plateaus or in the Hall conductivity are related to a topological invariant, but we have not elaborated it as yet. We are going to do that, but in order to understand that statement quite convincingly, what we do is that we change the system and we go to a system which has translational invariance such as a crystal lattice, and we want to see this in a crystal lattice what happens. Okay. Suppose we put a simple lattice such as a two-dimensional square lattice in a magnetic field, then what happens? Now, it is you cannot take a 1D lattice for discussing magnetic field, because we need to understand that there should be an area for the flux to penetrate in order to for that magnetic field to have any effect. A 1D lattice of course does not enclose such an area, and that is why we have to go to 2D, and the simplest of the 2D lattice is a 2D square lattice, a uniform square lattice, and that is what let us see that as I said, the idea is to understand the quantization of the Hall conductivity in terms of a topological invariant. This will yield sort of a mathematical way to arrive at that topological invariant that we just talked about, and this will make the calculations more clear. And otherwise, in a 2D electron gas, a dirty system and with no translational invariance, it is difficult to, or rather it is not possible to do a calculation. We just have to say that the topological invariant is the coefficient that sits in front of the Hall conductivity, and remember Hall conductivity has been found using Kubo formula, the formula that we have derived. Okay. Now, in order to talk about these periodic potential, let us understand the periodic potential. I have already shown that an electron is actually moving in a periodic lattice. So, it experiences a potential which is periodic in nature, that is it is of the form V of r equal to V of r plus r. Let us write a vector on everything where r is the periodicity. So, capital R is the distance between two successive ions, and they are offering a potential to the electron that is passing through it, and we have drawn a 1D lattice, but of course this can be done in any dimension. All right. The solution of this problem, that is, if you want to solve this one particle problem in presence of a periodic potential, this is called as chronic penny model. Solving the Schrodinger equation in presence of such a potential gives you the energy quantization for a problem which is a continuum problem. That's when the electrons have a k square type dispersion, a parabolic dispersion, h cross square k square over 2m. But in a lattice, the wave functions are given by a psi of r is equal to uk of r and exponential I k dot r, and this is the wave function. So this is a function of course k, and if you want to put a band index, because there are multiple bands that are going to form, and so we can put a n here and we can put a n here, where n denotes the band, so it's the first band or a second band and so on. So it's basically the band index, and these unk of r, it captures the periodicity of this potential that we have talked about. So k is actually a vector, so you can write down it as a vector, and so this is like a r plus r, and this goes by the name Bloch's theorem. But this is only half the problem. We need to also know about the energy eigenvalues for these periodic potential, and we can know it in a number of ways. And one of the things that are done in courses on solid state physics, or they are taught in that course on solid state physics, basic solid state physics, where you learn tight binding approximation. Okay. So, tight binding approximation means that the electronic wave functions are tightly bound to the ionic core, and it has very little overlap with the neighboring ions, but enough just to make the electron move from one position of one ionic core to the next. All right. So, let me give you a very simple derivation of this dispersion, the electronic dispersion, and in this particular case we just talk about a square lattice. So, a square lattice is the simplest thing. So, we draw a square, and let's just draw this, and every junction of this vertical and the horizontal lines, there is a lattice side that are present, and so this is that lattice. Say the lattice constant is A, and we are going to write down the tight binding dispersion, which is epsilon as a function of k. Of course, this is the real space structure. We are going to derive the dispersion in the momentum space, which is a function of k. And in order to do that, let me sort of resort to technique or formalism, which is like discretizing the Hamiltonian into a grid which is consisting of these lattice points. Okay. You can follow the derivation of this tight binding method for a general lattice, say for example a three-dimensional simple cubic lattice from Ashcroft. Okay. Let me show another way of doing it. Let's say we have a function on a 1D grid. Okay. So, there is a function f of x that resides on this grid, and this 1D grid is I am just talking about a 1D function, but it can be generalized to more than one dimension. There are these sides which are like, so these are there's no minus sign, there's just a dot dot, and then it's xm minus 1, xm and xm plus 1 and so on. So, this is the grid points, and this function is defined on those grid points. So, I can write it as xm, where m is any of the sides that you see written out here. Okay. So, what we can do is that since we are talking about a lattice, your xm and xm minus 1 or xm and xm plus 1, they are separated by a lattice constant a. What I mean by that is that you can write down this as so this is like a m minus 1 a, m a and m plus 1 and so on. Okay. This really denote the coordinates in a one-dimensional array. So, what I want to do is that want to evaluate derivatives. And you may ask this question that why do we want to evaluate derivatives, and the simple answer is that the second derivative, which is d2f dx square in this particular case, actually denotes the kinetic energy, because your kinetic energy is written as minus h square, h bar square over 2m, m being the particle mass, the mass of the particle that moves on this 1D lattice, and into d2 dx2. So, we want to discretize a d2 dx2 on a lattice, which gives you more intuitive way of connecting a continuum system and to that of a lattice. Okay. So, this you know from your elementary knowledge of derivatives. So, it is a df dx. Since we are talking about 1D, I can take the liberty of writing the full derivative. Otherwise, it could be, if you are talking about a two-dimensional system, so then it will be like a del f del x and so on. So, this is equal to f m plus 1 minus f of m minus 1. So, we are taking the 2-point difference formula. We are not taking f m plus 1 and f m, or f m minus 1 and f m, but we are taking this side and this side and then dividing it by 2a, and this is the formula for the derivatives, I mean the first derivative, so to say. Let me write down the second derivative. The second derivative, which is d2f dx2, of course this is a m, and this is written as fm plus 1 minus twice of fm. This is called as the 3-point formula and so on, and then fm minus 1 divided by a square, and these f's are the values of the function, and a is of course the lattice constant, or the distance between two successive points. Okay. So, we want to calculate the matrix element of the operator, either these d2f dx2 or df dx. Let me show for both between two sites m and n. So, it is a m d dx of n, mn actually denote sites. So, this is like m plus 1 n minus m minus 1 n. Okay. So, where f of m we are using that f of x m. So, this is the first derivative, or this the matrix elements of the operator ddx, and this is nothing but using the relations of the orthogonality relations. This is nothing but a delta n m plus 1, otherwise it will go to 0 if n is not equal to m plus 1, because these are kets. So, we are taking the basis to be the side basis m, okay, and taking the expectation value of these operator ddx and d2 dx2 in this basis, which is given by this. So, let me write that this is the basis of the problem, which is the side basis, okay, minus delta n m minus 1 divided by 2a. Okay. So, this is the ddx, and similarly we can do it for a double derivative, which is d2 dx2, which is this, and this is equal to again we can write it down. So, del n m plus 1, you can check that, minus delta n m plus delta n m minus 1 and s square. So, just to tell you that delta n m, this is called as a Kronecker delta. Okay. So, what is meant by Kronecker delta? That is the definition is, so if this is equal to 1 for m equal to n, it is equal to 0 for m not equal to n. That is when m and n become same, then there is it gives you a value 1, otherwise it gives you a value 0. Okay. So, this is what it means, and where it comes from is from the orthogonality relation like this, which is delta mn. So, these have matrix elements only between these states which are given by. So, single derivative only has matrix elements between the neighboring sides, either the left neighbor, which is this is m plus 1 is the right neighbor and m minus 1 is the left neighbor. And similarly, this has the d2 dx2 has matrix elements in between these 3 states, that is n equal to m, n equal to m plus 1, n equal to m minus 1. And you can understand that if I want to write down the double derivative in 2 dimensions, that is if I want to write dx2 plus a d2 dy2, and then I have to introduce another variable, say mn for x direction. I mean, m will denote for this x direction the coordinates in the x direction, and n will denote coordinates in the y direction, and then you have to have m prime and n prime in order to take the these matrix elements. All right. Let me write down a general operator A, and which has a form which is like mn, and this is like mn and cm dagger cn. Okay. I am introducing this fermionic operators. I mean, this could be fermionic, this could be bosonic, depending upon what is the context of the problem. Let us say we are talking about electrons, because that is under our discussion now. We are focusing on electronic transport. So, these are electronic operators, and they have the anti-commutation relations between them. So, which are given by a Cm and a Cn dagger, this is equal to delta Mn and so on. So, this means that this anti-commutation relation means that there is a plus sign between the two, that is Cm Cn dagger plus Cn dagger Cm. This is equal to delta Nm or Mn, does not matter. This tells you that we are really talking about the second quantized operators to describe the electron. So, this could be a Hamiltonian. I have just written any operator, it could be the Hamiltonian of the problem. So, if you use those definitions that we have just written above, so then this is equal to 1 over 2a, which can come out of the integral, and this is equal to like Cm plus 1 and minus Cm dagger. So, this is Cm dagger Cm plus 1, and this is a Cm dagger Cm minus 1, and so on. Okay, so this is the ddx operator, and similarly the d2 dx2 operator can be written in a similar fashion, which has a 1 over a square in the denominator, and you have a, and then you have a Cm dagger Cm plus 1 minus 2 Cm dagger Cm plus Cm dagger Cm minus 1, and I am just following these definitions that we have said. So, these we are discretizing the space, so that from a continuum system we are going into a lattice. So, we are using this discretization scheme in order to understand that how a kinetic energy, which was written as simply as minus h square by 2m and d2 dx2, how that can be written in a lattice. So, that is the idea behind this, and we are sort of proceeding in that direction. Okay. Just like what we wrote. So, h equal to p square over 2m, and in 3 dimension this is it's equal to minus h square over 2m and a d2 dx2 plus a d2 dy2 plus a d2 dz2. Okay. That is the operator, and if you have no potential, that is the only term that is there. Of course, in presence of a periodic potential, you will have a periodic term which is V of r. So, right now we are not talking about this V of r, we are focus on this now. All right. Okay, so of course, here what comes is that, so you have this h cross square over 2m, and then we have this n, and let me just write the only in one dimension. So, this and then n, because that will give me the energy, that is the expectation value. So, I am taking it between the same states, and this will give me equal to say a TNM, which is TNM is the hopping amplitude from site n to site m. Okay. So, that is your TNM. This is equal to, so you make an approximation that this is equal to T if n equal to m plus a delta, I mean a x cap, where x cap is the unit vector in the x direction, and as I said that n and m are just the site indices. So, if n happens to be m plus 1 unit, that is 1 lattice spacing, either in the plus direction or in the minus direction, and so on. So, this is equal to a plus and minus in 1D, or it is this thing if otherwise. So, you make this approximation, okay, or let us say this is the assumption, and which is also called as the tight binding approximation. I remind you that I have said that the approximation is that the electronic wave functions are strongly bound to the sites, and they have very little overlap with the neighboring sites, but just enough to give you a hopping from or a jump of the particle from one site to its neighboring site. Okay. So, this is of course your T is equal to nothing but equal to, in our language it is like h over 2 m a square and so on. And now in addition to this, if you consider these Cm and Cn operators, we can do a Fourier transform of this operators. It is just like the restatement of the Bloch's theorem for the operators, and in that case your Cm plus n is equal to exponential I k dot n, and let me write it in, since I am writing it in one dimension, let us not write with a vector sign because it is a one dimensional problem. So, this is equal to Cm, and if that is true, then of course your epsilon k, or the energy that comes from for this Hamiltonian. So, epsilon k is nothing but the energy or the eigenvalue of this Hamiltonian that is written in equation 1, but without the V of r. There is no V of r there, and this is equal to a minus 2t, including the minus sign. Now, it is equal to cosine kxa plus a cosine kya. Okay. In the sense that we are only dealing with the kinetic energy term, and so these kx etc., these are two dimensional. So, I have now written it in 2 dimension in a 2D square lattice. In 1 dimension, simply it gives you a minus 2t cosine kxa. I just went one step ahead, and in a square lattice with lattice constant a, I write this as, this is the energy dispersion. So, this is called as a tight binding energy dispersion. So, this was a missing link in the problem where you are talking about the electrons present in a periodic potential. So, this is the kinetic energy, this is how the kinetic energy behaves, and if you look at it carefully, your the long wavelength limit of this dispersion exactly looks like the continuum problem. So, if you take a long wavelength limit, which means that your k actually can be written as 2 pi over lambda, and which means lambda is large. So, k goes to 0 when lambda is large. So, that is the long wavelength. Okay. So, if k goes to 0, I can do a So, k going to 0 limit of this is minus 2t into 1 minus k x square over 2. This is the cosine function, that's how the cos behaves as you take the kx going to a 0 limit, kx of course a square and plus a 1 minus ky square by 2 a square and so on. So, this I take away this. So, this is equal to 4t minus 4t, 4t because there is a 1 and 1 that will make 2. So, 2 and 2 4t, and then there is a 2t and a square and the kx square plus a ky square. If I drop this term, neglect, what I mean is that it is a constant term which can be neglected. So, this really looks like the k squared dispersion which you are most familiar with. It is a free particle dispersion in k space, which is h cross square k square over 2m. Okay. So, the dispersion of electrons in 2 dimension in a 2 dimension square lattice is given as this minus 2t cosine kxa plus a cosine kya. Now, of course, the system has translational invariance. We will come back to this figure, you may be seeing this. This is one of the important discussions that will have to be done, and this is called as the Hofstadter butterfly, but I will come back to this. All right. So, now of course, one of the chief ingredients of our discussion is the magnetic field. So, we will let us do a square lattice in a magnetic field. Okay. And we write down again the Hamiltonian. So, it is in a square lattice. So, we have the Hamiltonian, the tight binding Hamiltonian. Now, we are not writing Mn, M was written because it was a single this thing. Let me write it as I and j, which means the same thing. And when I use this symbol Ij with an angular bracket, it means that they are nearest neighbor. So, j is the nearest neighbor of I. So, this is equal to, in principle you can have Tij to be inside, which means that it can be different, the hopping amplitudes can be different for each of the links in a square lattice. I have already shown you a square lattice. So, this is a C, Cj dagger, Ci, and now a magnetic field has to be included. And how do you include magnetic field? You have seen that in a continuum system it is included as E plus P plus Ea. So, it enters through the momentum of the particle. So, the magnetic field enters through the vector potential, and the vector potential actually renormalizes the value of the momentum. It makes the mechanical momentum to be the canonical momentum, which is nothing but P plus Ea. But in a lattice it enters just like this, that T, the hopping amplitude, it is a T into exponential some I and some phi. Phi is some phase, okay, and this phase contains the information about the magnetic field through the vector potential. So, this phi is nothing but it's related to the line integral of the vector potential, and if you use the Stokes theorem which says that the line integral of a vector potential is actually, or rather any vector is can be written as a curl of the vector and over this ds. Now, this is of course a closed integral, and so this S is the surface of the closed contour that you have considered. So, this curl is nothing but B. So, this becomes a B dot ds. So, this phase that you see involves the flux that threads through the lattice. So, the magnetic field has a flux which is given by the B into the area, and that whatever flux threads the sample or the system is given by this, that appears in the phase. Okay. So, there is a Hermitian conjugate, that is very important. We have not written it earlier, but because of the Hermitian conjugate, the Hamiltonian becomes Hermitian and it gives real eigenvalues. Okay. If you do not have that, then you have problems. Okay. Now, In presence of the magnetic field, we do not have translational invariance, and the reason that we lose translational invariance is because the hopping now becomes a function of ij, that is these sites, because as the electron hops, it picks up a phase and then it picks up another phase. Okay, I mean that phase keeps growing as you keep as the electron or as the particle keeps hopping from one side to another. Then of course the Hamiltonian, which only comprises of the kinetic energy or the hopping term, then is not same from going from one side to another, and if it's not same, then you cannot Fourier transform and write it epsilon as a function of k. But luckily there is something else that happens. We would be able to formulate a magnetic Brillouin zone or a magnetic unit cell, which of course does not have the periodicity, but that unit cell is repeated, which means that what I am trying to say is the following: exponential I phi is a phase, right? So phi is a phase which is just like an angle. Now if the phi changes from phi to phi plus 2 pi, so if the angle changes to 2 pi, then of course the phase does not change at all, because exponential I phi plus 2 pi is equal to same as exponential I phi, because exponential 2 pi I equal to 1, which is cos 2 pi plus I sin 2 pi. Okay. So because of this, even if the electron hoppings are different, but it is only different over certain dimension, and we can take that as a unit cell. See, previously the unit cell was just comprising of one atom, which we have shown here. So here, I mean, one lattice point you can frame a unit cell there, and you can translate it everywhere in order to generate the lattice. If you have a bipartite lattice, then of course you have to have two atoms per unit cell and so on. Okay, I am just doing a general discussion, but here you cannot generate the lattice, because the Hamiltonian being, it changes as you go from one side to another. So this picks up a phase which let us write it as theta ij. Okay. So as it goes from I to j, it picks up a phase. So there is a I here, and the reason that I am writing it with a red ink is because this is equal to, so I in red is root over minus 1, whereas the I in black is not other site indices. Okay. You do not have to carry on this ambiguity for too long. Will sort of and if it bothers you, please help yourself to write with m and n, okay, which is going to be fine. All right. And this phase factor theta ij equal to minus of theta ji. So basically it is defined on a link or on a bond. Okay. So it connecting pair of sites I and j. All right. So what is then a theta ij? Theta ij equal to 2 pi e over h, and from I to j, now these are of course sites, and this vector potential dot dl. Okay. And so A is the vector potential. So now what can be done is that this 1 over 2 pi, this 2 pi, if I take it down, and then I sum over all the theta ij's in going from these. So this, as I go in one this thing, so I go like this, then I go like this, then I go like this, and then I go like this. Why do I go in a particular placket? This is like called a placket. I go in a placket because in order to understand that what is the flux that thread, this is related to, these hoppings would be related to the flux that threads that particular this area which is shaded like this. Okay. So, in order to do that, let us sum over all this around a placket area. Let us write it like this, and this is equal to nothing but E over H and then integral, I mean the closed integral A dot dl, and so this is H. So, E over H, H over E is, just to remind you, this I have done several times, this is the flux quantum, let us call it a phi naught, which has a value which I have told also a number of times. Okay. So, this is equal to 1 over phi 0, because E over H is inverse of H over E, and then there is a surface, and then this is equal to B dot ds. Okay. So, as I just said that these phases are related to the flux. So, B dot ds is a flux that threads one placket of that square lattice which I have shown, and phi 0 is of course the flux quantum around this placket. So, we know this. So, this is actually the phi. So, let me write this as phi over phi 0, and that is equal to 1 over 2 pi and then sum over all this theta I j and so on. So, suppose this phi that you have here, this flux B dot ds. So, this phi which is let us call it as a 1 over 2 pi and then this theta I j over a placket. I am just in shorthand, I am just writing a bracket that is around a placket. So, this becomes equal to, or rather this phi over phi 0, it becomes a fraction like this. So, P by Q is called as a rational fraction when P and Q are co-prime integers. And what I mean by co-prime integers is that basically they have no a common quotient, that is one cannot be divided by the other, such as say 1 by 3, 2 by 3, 3 by 5 and so on, 3 by 7th and so on. So, there is no common factor, and that is why they are called co-prime, and this is a rational fraction. Okay. So, if it is in this form, because phi by phi 0 is a fraction, and if this fraction happens to be a rational fraction, in that case then the spectrum that I have shown, this is quite important, splits into Q subbands. Okay. And so, basically somebody called D. Hofstadter he studied this problem for the first time, and that is why these quantization of the electronic dispersion, which is minus 2t cosine kxa plus cosine kya, which is which just saw. Now, that further splits into these subbands and it forms a fractal structure. Okay. I will show you the picture, but you will have to calculate, work out that and calculate this thing. And so, suppose now our job is to take a specific choice of magnetic field. That is easy, because we have several times said that we want to take a B, which is B z cap. Okay. And then of course, we have one of the choices, which is a Landau gauge. So, let us write a Landau gauge. So, this is equal to B x y cap. Okay, or you can take B y x cap. Now, because of this, let us see what happens. Let me draw this square lattice once again, and you will see that Just bear with me till I draw the lattice. These are the bonds along with which the electron hops, or the links, you can call them a links or bonds, and so on and so forth. Well, I think this should be enough for our discussion. Okay, all right. So now what happens is that you see the hopping in the x direction is unchanged, okay, because the gauge is in the y direction. So the theta or the phase that the electron picks up will only be affecting the movement in the or hopping along the y direction. So the x direction still remains as t, t, t and t. Now let me take for L equal to 1. So these are different rungs and different legs and rungs. So L stands for leg, and this is L minus 1th leg, this is L minus 2th leg, this is L plus 1th leg, and so on. So this is k equal to minus 1 rung, and k equal to 0 rung, and k equal to 1, and k equal to 2, and k equal to 3, and so on. Okay. Now these hoppings are like t in the x direction. In all the x direction is t, because the gauge is particularly taken in the y direction, because it's bx y cap. Okay. And because of that, these hoppings along these y directions, they will pick up a phase. This directions it will pick up a phase, and they will pick up a phase depending upon this phi by phi 0. Okay. In a particular case, let us take phi by phi 0, a rational fraction, a specific rational fraction 1/3, which is simple. Okay. So then what will happen to these hopping? So this hopping will be t into exponential 2 pi I by 3, t exponential 2 pi I by 3, t exponential 2 pi I by 3, and so on. So this will be at k equal to 0 will be still t, of course, because this is we are talking about. So this will be like t exponential 4 pi I by 3, t exponential 4 pi I by 3, t exponential 4 pi I by 3, and so on. And similarly, there will be t exponential 4 pi I by 3 along these bonds. Okay. So t exponential 4 pi I by 3 and t exponential 4 pi I by 3, and so on, and all the horizontal hoppings are of course t. Okay. Now you see your B is in the z direction, that is it is coming out from the board. Okay. So you see the point dot of the arrow, and this thing is in the y direction, of course, and but it's increasing in the x direction like this, and so on. So this is the A. This is the x direction, because it's b into x, and it's increasing in the y direction. So this is not the direction, this is x, because as x increases, b increases. Okay. So we have particularly taken the p by q equal to 1/3, okay, and have done this. Now you see why I have drawn it till this and not drawn in beyond this, that is not one more sequence of sites. And the reason is the following, that you see the next thing, if suppose there is one here and here and here, let me sort of show it by some. The hopping would have been 6 pi I by 3 in that along the y direction, and 6 pi I by 3 is nothing but 2 pi I. So that will be the same hopping that we have started with here. Okay. And so on. Okay, I mean just check that whether everything has been written correctly, but when the hopping becomes 6 pi I by 3, it becomes equal to 2 pi I, and which is same as t. So we are able to identify a magnetic unit cell, which, I mean, this is the magnetic unit cell for this choice of flux, which repeats. So, it starts with okay, maybe I will sort of take this thing also, because it starts with t in the vertical direction and then it sort of carries on. So, it is t in the vertical direction is t 2 pi I by 3 and then it is t 4 pi I by 3. So, possibly we will just remove this and check what they are in this particular. So, it is k equal to 1. So, it should have been minus 2 pi I by 3 and so on. Might have written it wrong, but check what they be. And so, this is the unit cell of this problem. And now, even if the system has lost translational invariance because of the presence of the magnetic field, we still are able to calculate, or rather take a unit cell and diagonalize that Hamiltonian. Okay? And one such exercise one can do, in which I have taken a slightly different unit cell, that is I have taken p by q equal to 4, that is 1 over 4. So, written down a Hamiltonian, which is so there is a minus 2t cosine of say b a plus k y a, and so this is including all of that. So, t exponential I k x a 0 t minus I t k x a, and there is a t e to the power minus I k x a, then there is a minus 2 t cosine, this is all minus signs, cosine b a plus 2 b a rather k y a, and minus t exponential I k x a, and a 0 and a 0 here. So, let me show you a specific example where we deviate from the earlier example and take another fraction, another rational fraction for this phi over phi 0, which is of the form p by q, and let me take it as 1 over 4, which is another rational fraction that we talk about. Now, that of course, the unit cell, the magnetic unit cell will comprise of 4 terms, or rather 4 lattice sides, and hence we can write down a 4 by 4 matrix. So, the matrix one can check that the matrix looks like this, and it is a 4 by 4 because there are terms which are on site terms, and then there are terms which are across the sites and so on. So, these are terms, and then when you solve this, one gets 4 eigenvalues, and let us write down the 4 eigenvalues. Let us write them as so, it is minus 2 t cosine k x a plus 2 t cosine k y a, lambda 2 equal to 2 t cosine k x a plus 2 t cosine k y a. So, this is k y a, and lambda 3 equal to 2 t cosine k x a minus 2 t sine k y a, and lambda 4 equal to 2 t cosine k x a plus 2 t sine k y a, and so on. Okay. These are the 4 eigenvalues which you can solve using either Mathematica or MATLAB or Python. And once when you do this and plot the energy, so these are the energies of these magnetic unit cell, and when you do that for a large number of values of the magnetic field, you get a spectrum which looks like this. This is called as the Hofstadter butterfly. this is actually fractal in nature because there is a self-similar structure. So, if you read on fractals, basically a small part of that looks like the whole picture that you see here. So, whether you see it here or you see it here, everywhere there is a structures are self-repeating, and this is called as a fractal. Okay. And these fractal structures, or these in the energy as a function of phi by phi 0, this is the same phi by phi 0 that we have talked about. So, these for different values of the flux. So, we have shown for one value of phi by phi 0 all these results. If you do it as a function of phi over phi 0, then the E in terms of this T is or T naught is the scale of the problem, and one sees a fractal nature. And so, our job is not to really dwell on the Hofstadter butterfly, but this is one of the things that arise for these energy spectrum in presence of a magnetic field, where the tight binding dispersion itself splits up, each of the bands split up. If there are multiple bands for a given problem, they split up into these self-similar structures as a function of phi over phi 0 or p by q. You see all those fractions were taken. It's another piece of information that the quantization of the Hall conductivity can be captured from these gaps in the spectrum through a formula called as a Streda formula. Will not worry too much about that, because we have other ways of calculating the Hall conductivity and so on. So, we will leave that and carry on the discussion. Will not do a sort of completely elaborate study of the spectrum in case of graphene, but we want to see how the situation evolves when you have graphene. So, we will talk about graphene and graphene in magnetic fields.